Good evening to all. So let's see what we have done in the last session. So in the last session, we have basically touched upon the virtual memory segmentation. In case of virtual memory segmentation, your segment table is similar to your normal segmentation table where you have segment number and length. But along with that, you have two more bits as normal paging. You have present bit and modify bit. So the present bit will check whether the current segment that you are trying to access is in the memory or not, in the main memory or not, so is present or not. And the modify bit will check whether the contents of this segment is modified or not since it was last loaded. So the use of modify bit is that if modify bit is set to 1, then at the time of swap out, when you swap out that particular segment from the memory, you have to perform the disk write operation first. You have to change the content of the particular segment in the secondary memory before you can discard that page. But the overall advantage of virtual memory is, to summarize, the overall advantage of virtual memory is that the page or the segment that you are trying to access all page or segments of the process may not be in the main memory. So this is the overall concept of segmentation or paging in virtual memory scheme, that your paging and segmentation remains as it is, but all pages and all segmentations of the process need not to be in the main memory in order to execute a process. After that, we have seen a relationship between page size and page fault rate. So we have seen that as the page size increases, the page fault rate will also increase, and it will be saturated at one point, and later on it will start decreasing and it will reach to 0 when basically page size is equal to process size. Similarly, the second parameter we have seen was the page fault rate versus number of frames allocated. So if the number of page frames allocated to the process is smaller, then page fault will also be high. But as you increase number of page frames allocated to the process, so eventually the page fault rate will be basically it will drop and it will be 0 to increase the number of page frames. We have seen the discussion on TLB, the translation look aside buffer. So TLB is a kind of cache mechanism which acts as a cache to store your recently accessed page table entries. So remember that TLB is a cache of page table entries. So whichever entries are accessed very frequently, they are stored in cache. So later on, if they are accessed again, so you can directly find the physical address from the cache memory, from the TLB, rather than going to the main memory. So we have seen one flow chart. Let me present that. Yeah, so this was a flow chart. If you remember, this is very important. One of the very important concepts from this chapter, that how the address translation is done if you are using virtual memory paging along with TLB. So first it will check TLB. If the address is found from TLB, generate it. Otherwise, look into the page table. If the particular page is not present in the memory, then generate a page fault and get the page from the secondary memory, update the page table and update the TLB. It's kind of overview. And the last topic, in the last lecture, we have seen the combined approach of segmentation and paging. So in this combined approach, uh, as you can see, the process was divided into unequal size of segments. So suppose I have this process A. So process A is physically divided into segments. Those segments are unequal in length, like this is one segment, then this is another segment, maybe this third segment, like this. And after that, each segment is divided into pages. So what happens is each segment is divided into pages. So if you want to access individual segment, then within the segment there is a paging. So for each segment, you have to maintain one page table. For each segment, you have to maintain one page table. So here you can see segment table entry contains starting address corresponding to the segment in the memory, length of the segment, then a bit, whether the segment is present in the memory or not, another bit for knowing the modified bit or not. Apart from that, this is the address translation diagram in case of combined paging and segmentation scheme. So here you can see the virtual address consists of three parts: segment number, page number, and offset. So from the segment number, we will find out the corresponding segment of the process, like segment 1, 2, 3, 4. In our example, in the previous example which I have presented just now, I have 4 segments. So one of that segment is referred here. So from the segment table, I will get the details of I'll give the details of segment number to the segment table. So from this, I will get the address of the corresponding page table. From that, I will get the corresponding address of the page table, right? Because for each segment, there is one page table, right? For each segment, there is one page table. So here, at this particular step, I'm getting the address of the page table, which I have to refer. And in that page table, I have to look for this page. So this address is transferred here. So if I combine these two things from here, I will actually get the frame number and offset. So you can see that we are taking the advantage of both structures, segmentation and paging. On one hand, segmentation is a transferred to the user. Similarly, paging has its own advantage. So in this kind of combined architecture, we have to combine both segmentation and paging to utilize the benefits of both. Right? To utilize the benefits of both, we have to combine these both architectures. So as you can see, this particular structure can give you benefits of both segmentation and paging. But as you see, as you increase more and more components, the hardware complexity is increasing. The hardware complexity increases proportional to the complexity that you include in your circuit, in your address translation mechanism. So if we talk about hardware, here you require two things: segment table, page table, segment table based register, page table register, then a data structure to store both segments and pages. So simple segmentation and paging was the easiest one to implement and lowest in terms of complexity, and virtual memory paging and segmentation little difficult to implement because you have a constraint that if all the pages are not present in the memory, then also you can execute the process. And at last, we have this combined scheme of segmentation and paging, which may be very complex to implement if we think about it. So if we talk about protection and sharing, segmentation lends itself to implementation of protection and sharing policies. So it is very compatible to implement various security policies if you are using segmentation. For example, you can make a particular segment shared. You can make it private. That is one thing. Then you can easily protect some segment from other segment. All these things can be done easily. As each entry has a base address and length, it is inadvertent memory access can be controlled. You can control how the addresses are accessed because you have length parameter. So when I access any segment, I have length information. So I know that this is the valid length of the segment. If I'm making a reference which is above that, then it's not going to be a valid address. So in that way, segmentation is more what you say protection friendly, right? Segmentation is more protection friendly, sharing friendly, and security mechanisms you can implement easily. So till now we have been discussing about the hardware aspect mostly for the virtual memory and the relevant concepts. So all these things like page table, segment table, they are hardware related issues, and operating system needs to depend on underlying hardware for the support of the particular features. In the remaining half of this chapter, we are going to discuss softwares or kind of various algorithms which are being used along with the virtual memory scheme so that the overall implementation can be easy and can be efficient. So what will be our point of discussion? Before that, we just look at the decisions that we take when we use the virtual memory. The first decision we have to take is very simple, is whether to take a virtual memory or not. So whether we should use virtual memory in our system or we should not use. That is the first decision. In case of single memory, in case of normal memory, you are assuming that all your pages and all your segments are present in the memory. If you want to access a particular process, if you want to um, kind of execute entire process. In case of virtual memory, only few segments or few pages, if they are present in the memory, then also you are fine. So first decision is we have to just kind of see that whether we want to use virtual address or not. Second decision we have to take is the use of paging or segmentation or both. So are we going to use normal paging, virtual memory paging, segmentation, or we want to use the combined scheme of paging and segmentation that we have to see. That is the second uh, decision that we have to take. And the third decision is the algorithms employed for various aspects of memory management. So this is what we are going to see in the upcoming discussion in today's session. So we look at the various policies and algorithms that are employed along with the memory management scheme to make it more efficient. And also we will have different algorithms, different designs, and we will compare each algorithm, its performance with respect to the memory management scheme that we are using. So what kind of decisions or we have to take, and what kind of policies or algorithms we are going to study. So this is the overall idea of our uh, topics for the next discussion. So we see first fetch policy. First see the fetch policy. Fetch means when to fetch a new program or process in the memory, one aspect. Second aspect is when you want a certain data, do you fetch it at that time or you fetch it in advance? So these are two decisions that you have to take in case of fetch policy. Then placement policy. So where in your memory you are going to keep your pages and segmentation. There is a placement policy. Then replacement policy, very important this topic, replacement policy. What is the meaning of replacement policy? Let's say X number of pages of some process are there in the memory, and you want to bring more pages, but there is no room. There is no room for the new process, for new pages. So what you do, some of the existing pages, one or more pages you have to swap out. One or more pages you have to swap out. That decision, which page you have to swap out, is called replacement policy. So we have different algorithms on replacement policies like FIFO, LRU, and so on. After that, we will see resident set management. So as you know, resident set means the set of pages for a process which are there in the memory. In order to execute the process, whichever pages are required is called resident set management. So different policy level discussions with respect to resident set that we will do. Then cleaning policy, when you terminate a process, how do you clean your memory? So cleaning policy, and finally we'll see load control, at what is the degree of how to maintain degree of multi-programming in your system. So this will be the overall agenda for the discussion. So we are going to complete this discussion in today's session and next session. And during the next session, whatever time is remaining, I will discuss few examples of paging and segmentation, which may be helpful from the exam perspective or any other exams that you are preparing, such as GATE exam. There is a lot of weightage of operating system in GATE exam as well, and frequently the questions of memory management are asked. So I will select few problems and we can discuss it during the next session. So this session and next session we have to spend on this virtual memory. After that, we will start the discussion on concurrency control. Anyways, so let's look at the policies one by one. So first is fetch policy. So meaning of fetch policy, as I told you, to determine when a page should be brought into the memory. When a page should be brought into a memory. So you see, virtual memory concept, it means that only few pages are there in the memory. Remaining pages are there on the secondary memory. If I talk about, let's say, process A, let's say process A has 10 pages. From the 10 pages, 5 pages are in main memory. 5 pages are in main memory. Remaining 5 pages are in the secondary memory. And my process can still execute because some of the pages are there in the main memory. According to the philosophy of virtual memory, my page can process can execute. But these pages which are there in the secondary memory, 6, 7, 8, 9, and 10, when do you bring it to the main memory? This decision is taken as a part of fetch policy. So we have two different fetch policies. One is called demand paging and second is called pre-paging. Now, very simple thing, if you don't know anything, then also you can understand. Demand paging means as and when required. As and when a particular page is required, you have to fetch it. You have to fetch that page. Okay. And what is pre-paging? In case of pre-paging, irrespective of the requirement, you bring some pages into the memory in advance. So that is your pre-paging. So formally, let us see demand paging and pre-paging. In case of demand paging, only bring the pages into memory when a reference is made to a location on the page. Simple. So whenever that particular page is being referenced, only at that time you have to bring it to the memory as per demand paging. And the concept of demand paging is that many page faults are there when the process is first started. Why? Because when the process is first started, only few pages are there in the memory. So there will be a lot of page faults and you cannot bring new pages in advance because you are using demand paging. So as and when the new pages will be requested, they will be brought into the memory. So initially there will be many page faults. So if you want to look at the another design called pre-paging. Now what is pre-paging? In case of pre-paging, you bring one or more pages that is needed and even bring more pages than the needed. Right? So whichever pages are needed, you have to bring some more pages than the required pages. So basically more efficient to bring in the pages that reside contiguously on the disk, right? So whichever pages are residing contiguously on the disk, that you have to bring in case of pre-paging. Pre-paging is not swapping. In swapping, you bring the new pages only when the current page is to be swapped out. But in case of pre-paging, you bring some pages. Suppose you require 3 pages, but in case if you are using pre-paging, then you bring 10 pages, right? So 7 additional pages you have to bring. Okay, you have to bring 7 additional pages in case of pre-paging. Okay. So definitely demand paging and pre-paging have their own advantages and disadvantages. So while demand paging has many page faults when it is started, and pre-paging have less page faults, but on the other hand, the disadvantage of pre-paging is that you require more space than the needed, right? You require more space than the needed space, because if you require 5 pages and then you bring 10, then you require additional memory to uh, accommodate those pages. But if performance is faster, right? Performance is faster. So in case of pre-paging, there will be less page faults and faster access, less page faults and faster access. In case of demand paging, many page faults and slow execution. So this is about demand paging and pre-paging in your patch policy. The next policy is placement policy. So placement policy kind of determines where in your real memory a process piece is to reside, right? So basically, the decision whether to where to put a page in in a memory depends on segmentation or paging, which scheme you are using. So if you are using pure segmentation, then you can use best fit, first fit, or next fit algorithm. You already know these algorithms, right? In the case of placement algorithms, we have discussed this before your exams. So these algorithms you can use to allocate a page to a memory. So this placement policy basically it is what? It is allocation of your pages to the memory, right? The allocation of your pages to the memory, that is your placement policy. If you are using paging or combined paging and segmentation, then this thing is managed by hardware and placement is irrelevant. Why? Because in paging there is a fixed size of pages and similar size of page frames. So it doesn't actually serve a purpose that where you are placing your page or segment in your memory if you are using combined approach. So just quick quick recap is that if you are using pure segmentation, then you can use the algorithms like first fit, next fit, best fit. If you are using paging or combined paging with segmentation, it is to be decided by hardware. So this is related to your placement policy. After placement policy, we come to a very important concept of replacement policy. So what is replacement policy? So as you read from the slides, when all of the frames are in the main memory, those are occupied and it's necessary to bring a new page. So some of the pages from your memory should be replaced, and this is actually the meaning of page replacement. I think it is very intuitive to understand, but still, all right. Suppose this is my main memory, and as you know, main memory is divided into frames. So these are the frames. Now all frames have been occupied by some pages X, Y, Z, P, Q, R, S, T, U, right? These are the pages which are occupied in the frames. So this is actually your main memory, and these are the pages. Now what? Let's say there is another process, process Z, and you want to bring in some page of process Z to this memory, but all the frames are occupied, so you cannot bring it directly. So what you have to do? You have to swap out one page. So let's say you let's call it Z2 because Z is already there. So what you do, you swap out some page. Let's say you say that I will swap out P. So P will go out. P will go out, and Z2 will come in here. So this going of P out is called page replacement. Called page replacement. And out of all the pages, why you selected this P page for the replacement? This decision is called the page replacement algorithm. So page replacement algorithm, see, very simple. When you want to replace a page, you have so many pages in the memory. You have to decide that which page I have to swap out. This decision is called page replacement. So the discussion is which page you have to replace. When you replace a page, it should be the page that is least likely to be recalled in the near future. This is a very important consideration, right? Because if you replace a page, if you move some page out of the memory, and the next timestamp it is required, on the next timestamp it is required. So how are you going to kind of how are you going to access that page again? So it's not a good idea to replace a page which is not referred, which is referred in a near future, near past. So deciding on this, you have multiple algorithms, but you have to keep principle of locality in mind when you do this. So when you do the replacement, you have to consider key aspects. Number of frames to be allocated to each process. Like you should not be very partial. So try to allocate equal number of frames to each process so that the overall scheme remains fair to all the process. Also, candidate set of pages can be either from the process causing the page fault or from all processes in the main memory. So this is also important, right? Suppose you have, as in my previous example, let's take a very simple example. Suppose you have process A process A's page A.1. A1.2, C1, C.1, and C.3, right? D.1. This is your main memory. A means process A, right? And 1 means page number 1. Now let's say A.3 you want to swap in. You want to swap in A.3. Okay. So one way to look at it is that since process A is creating a page fault, I have to swap out either A1 or A2, right? Because it is the process A which is causing this swap out operation. So I have to swap out this A1, A.1 and A.2. Another way is that I can also swap out D1 and bring A3. So then you can argue that, see, D is not causing any problem. D is not causing any problem to the system. then why D has to swap out? That is the decision, that whether you will swap out the page from the process which is generating a page first, or you can select any other process. Also, out of the selected set of pages, which page should be replaced? So, like if we have selected A.1 and A.2, so which one you will replace, A1 or A2? So all these decisions you have to take during the page replacement algorithm. However, we are going to focus only on the third decision, that if you have number of pages available in the memory, then which page you will select for swap out. That decision is called the replacement policy, which is what we are going to see. So before replacement policy, there is one more topic of frame locking. So what is the meaning of frame locking? So if some frame is locked, it means that it may not be replaced. It may not be replaced. Why? Why can be many reasons. One is kernel of the operating system, right? Is a crucial page frame which is containing crucial data. If you replace that, then your function of the overall system may be disturbed. So you should not kind of swap out that page, right? So that is a good decision you have to take. If the frame is locked, then leave it. Don't consider it for the replacement, right? So again, you see that I'm not using the word page locking. I'm using the word frame locking. So in the main memory, there are some frames which are locked, right? Which you cannot swap out, and such frames are called locked frames. How do you technically implement it? So for implementation, you have to associate a lock bit with each frame. With each frame, you have to associate one lock bit. So when that lock bit is set, it means that that frame is locked. You cannot swap it. Okay. So now we see important algorithms related to the page replacement. So these algorithms are called page replacement policies or page replacement algorithms. So we have FIFO, a very simple FIFO, LRU, least recently used, then clock, and then optimal. Now optimal is only theory, cannot be implemented. Because optimal requires knowledge of future, which is not quite possible to get it. So what is the meaning of optimal? It means that you look at the all future references of the memory. You look at the all future references of the memory and see that whichever page or whichever frame is not going to be used in future, you have to only swap that out. You have to only swap that particular page. So it's not quite possible. But let's see the other algorithms along with the tracing step by step. So consider a page reference stream followed by a executing program as this 232152453252. So what is this? It is sequence of references, page number. So it means that first I require page number 2, then 3, then 2, then 1, then 5, then 2. Okay. So from this sequence, I have to predict that if I want to replace one page, right? Let's say if I want to bring new page 6 to my memory, which page I have to replace? So I have many candidates, 2, 3, 1, 5, 4. Okay, so out of this, which page I have to select, which page I have to remove and bring 6 in. So for this you have algorithms, right? Now from this you can see that 2 is very frequently accessed, so you should not swap that out. Uh, that is very obvious. But how to formally do it? Let's see. So first, let's see optimal policy. It is, as I told you, it is only theory, cannot be realized in practice. So the optimal policy basically selects for the replacement that page for which the time to the next reference is the longest. Okay. So basically it means that I have to see the future and tell that whether this particular page is going to be referenced in future or not. If yes, then when it is going to be referenced. And based on that, I will decide whether to swap that or not. So again, it's not possible because we live in current time. So we have references of a process. We cannot look in the future and determine that which pages will be required and which pages will not be required. So that's why optimal policy is not the practical policy to implement. But we can see the example. So see step by step. This is very important. How to solve the example. In theory, you can also do the optimal policy. So you see the first reference is 2. Now here important thing to understand is that uh, number of frames are 3, right? Right. So for this particular process, I have assigned 3 frames. That means at max, at a given time, I can have 3 pages of this process in the memory. I can have 3 pages at max of this particular page in the memory, of this process in the memory. So initially we assume that all the frames are empty. So we bring the page number 2 in, we bring the 3 in, then again 2. So 2 is already there, so no need to do anything. Then 1. So this is the scenario, 2, 3 and 1. Okay. So up to this, everything is okay. Now our next reference is 5. See, our next reference is 5. So if you see the 5 is not present, so I have to bring 5 in and I have to remove one of the pages from here. So which page I have to remove? Can I remove 2? Can I remove 3 or can I remove 1? So for this, suppose for this example, since our policy, this example is of optimal policy. So we have to look at the future. Okay, you have to look at the future and see the references of 2, 3 and 1. So you can see 2 is referenced here only. So I cannot swap 2. 3 is also referenced here. 1 is not referenced in future. Right? 1 is not referenced in future. So you have to select a page which is referenced very late in future or if it is not referenced. So based on that, I select 1 and bring 5 here. And whenever I do swapping, I have to generate a page fault. What is the meaning of page fault? It means that I want to bring 5 in, but 5 is not present in the current scenario. So it is a page fault, right? So one page fault I have. Next reference is 2, but 2 is already here. So we are fine. Next reference is 4 now. Now again, 4 is not there in the memory. So it will be a page fault. It will be a page fault. And here I have to again select between 2, 3 and 5. So I have to look at the future again. I have to look at the future again and determine which page I have to swap out, 2, 3 or 5. So if you look at the future, 5 is reference very near future. Then after 3 is also reference. 2 is referenced relatively late. 2 is referenced relatively late. So what you have to do? You have to swap out 2, right? So are you getting what you have to do? Look at the future and see the timings of the references. Whichever page is referenced very late or not referenced, that you have to swap out. So you can see that here I am swapping out 2 and instead of 2 I am bringing in 4. Again the next reference is 5, which is already there in the memory, no issues. Next reference is 3, so 3 is also there in the memory, no issues. Next reference is 2 again. So 2 is not present in the memory. So I will generate a page fault. We have to generate a page fault. And when I generate a page fault, I have to again look at the 3 available pages, 4, 3 and 5. So if I see the future, 5 is reference, so I should not touch 5. 2 is reference, right? Then after that 2 is referenced. So that is another reference. So from 4, 3 and 5, 5 is reference, but 3 and 4 are not reference. So what I do, I keep 3 as it is, 5 as it is, and instead of 4, I bring in 2, right? Because 4 was the first page, so it is not referenced in future. So I'll swap out 4 and bring 2. So this is my third page fault. And after that, next reference is 5. So 5 is already present, and after that 2, so 2 is also present. So if you see the number of page faults, that is important point to consider this page replacement. Uh, number of page faults is equal to 3 in this case. And what is the page fault rate? So it means that how many references did you make? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So out of 12 references, there were 3 page faults. So 1 by 4 or 0.25 is the page fault rate. So I can say that 25% of the requests are resulting into a page fault. But as I discussed earlier, this optimal policy is not a good policy for implementation. It requires the knowledge of future, which is not quite feasible. So that's why we have another popular approach that's called least recently used. So now if you cannot look in future, at least we can look in the past. So look in the past and find out the least recently used page. Okay, least recently used means whichever page is used very older, right? Whichever pages are used in near past, we have to keep it, and whichever pages is used since very long time, whichever page is not used since very long time, we have to discard it, right? That's what we do in our daily life also, right? If you want to discard some item, you will see its usefulness, whether it is useful or not. If it is not useful in near past, then you can discard it. But if you require some item every day, then you will not discard it because you are afraid that it is required every day. So what will I do without that item? So it's LRU like this. On the implementation side, we observe that LRU is difficult to implement. Why? Because we have to keep track of the history of, we have to keep track of the past, that which items were referenced, which items were not referenced. That history we have to keep track. So it's kind of overhead, but there are different alternatives to implement this LRU. As mentioned here, one of the approach is to tag each page with the time of the last reference. It's like last access time. With every page, we have last access time. So when we are doing swapping, we'll see whichever page was not used in near past, we can swap that. So see the example of LRU. So example of LRU. So again, initially 2. So 2 is brought into the memory, then 3, then again 2 already present, then 1. So 1. So now the situation is this: 2, 3, 1. Now next reference is 5. So since 5 is not present, I'll generate a page fault. Since 5 is not present, I have to generate a page fault. Now I have to select between these three frames, 2, 3, and 1, which page I will swap out. So see, for that I have to look in the past. Okay. Now instead of future, you have to look in the past. So while looking in the past, you will see that 2 is very recently used. 2 is very recently used. You cannot swap it out. 3 is also recently used, but 1 is not there. Oh, sorry, 1 is here. 1 was very recently used, then 2 was used, and then 3 was used. So which was least recently used? This 3. Okay, 1 was used very recently, then 2 was used, then 3 was used. So based on this logic, you select 3 and replace 3 with 5. Okay, I hope you are getting. Logic remains the same between optimal and LRU, but in optimal you look in the future. In case of LRU, you look in the past. Okay. Now what we will do next is, next again we have 2. So 2 is already present here. 2 is present. Then 4. So 4 is not present. So I will again generate page fault. And I have to select between 2, 5, and 1. So if I see the past, then 2 was very recently used. 5 was also used, but 1 was used least recently, right? So in compared to 2, 5, and 1, 1 was referenced before some time, and 2 and 5 were recently used. So what we will do, we will swap out 1. Instead of 1, we could put 4. Then 5 is already there, no issues. Then 3. After 5, we have 3. So again, 3 is not present here, so we generate a page fault. And we look for 3 now. To insert 3, we look 2, 5, and 4. So you can see 5 was referenced here. 4 was also referenced. So 2 is least recently used. So we just swap out 2 and bring 3. 5 and 4 remains as it is. Next, I require 2. But 2 is not present here. So again, it is a page fault. So I have to search again. If you see 3 was recently used, then 5 was used, and then 4 was used. So 4 is least recently used. So I can swap out 4 and bring 2. After that, next reference is 5, which is already present, and then 2 is also already present. So basically, number of page faults are 4, and page fault rate is 4 by 12, that is 0.3. Okay, that is 0.3. So if you recall in the previous example, our page fault rate was 0.25, and here it is 0.3. So we have more page faults if you use the LRU compared to optimal policy, obviously. In the last policy for the discussion is FIFO, or first in, first out. So by far it is the simplest replacement policy to implement FIFO. As the name suggests, it works on out principle. So it treats page frames allocated to a process as circular buffer. It is very simplest policy to implement, and its replacement logic is that whichever page that has been in the memory for the long time, it has to be replaced. You remember FCFS policy of process? Similar to this, right? Means that whichever page came first, it will be swapped out first. And whichever page came last, it will be swapped out at last. So simple and kind of fair policy in order is FIFO, or first in, first out. So try to trace this example yourself. Let me trace it for 1 or 2 timestamps. So initial references are fine, 2, 3, 2, 1. Those references are fine. After that, which is the next reference which is causing the page fault? It is 5. Right? So 5 is causing page fault. So when I look at 5, I have to select one replacement from 2, 3, and 1. So what I will see which page came first. So you see who came first, 2, 3, or 1. So if we see 2 came first, right? So we will directly take 2 and bring in 5. And this is our page point. So like this, the policy goes on, and it will generate different candidates for the replacement. Let me trace one more. So again, we require 2, but 5, 3, and 1 are there. 2 is not there, so it is a page fault. Now, which page you will select? 5, 3, and 1. So who came first? In 5, 3, and 1, who came first? So you see 3 came first, right? So I will just uh, cancel 3 and bring 2. So if you continue like this, I'm sure that you will be able to trace this entire example. So I'm not going to trace it fully here, but at the end, you have to make an observation, and that observation is that there are 6 page faults. There are 6 page faults. So if we uh, look at the page faults look at the page fault rate for individual policy, you see that optimal policy page fault rate was 50% for, sorry, it was 25%. For LRU, it was 30%, but for FIFO, it is much higher, it is 50%. So you can see that page fault rate highly increases in case of FIFO. So it's also obvious because FIFO has no logic. It's not looking logically. It's only looking the time at which a particular, it only looks at the time uh, at which the particular page came, or it came first, it came late, like this. So this is the discussion about FIFO, LRU, and optimal policy. FIFO has highest page fault rate, whereas the optimal has lowest page faults. So one more policy which is quite popular is, given as an alternative to this FIFO and LRU, which is called clock policy. Now clock policy is very popular because of a reason. For the reason we see here, let me try to make an example. Yeah. So if you see here, if you look at this particular time, I have swapped out page number 2, right? I have swapped out page number 2, but you can see that in very near future 2 was referenced, and at that time I had to generate a page fault, right? So because I was not sure about the future, based on my policy, I swapped out number 2, but eventually it was required in a very short time. So this is not a good thing. So to solve such a scenario, we have a clock policy. What is clock policy? So clock policy, as mentioned here, uses one additional bit called use bit. So when the page is loaded in the memory for the first time, or it is referenced subsequent times, then the use bit is set to 1, right? So it's kind of indication that a particular page is being active, right? Whether it is loaded for the first time or it is in use, right? Some process has already accessed it. So it is use bit in that sense. Now, when it is time to replace a page, when it is time to replace a page, the OS scans the set, flipping all ones to zeros, right? So this is very important. It's like it will scan all the pages, and wherever the use bit is 1. So what is the meaning of use bit 1? It means that this page is active. So it will not, OS will not swap it, but it will make that 1 to 0. So it is just giving a warning that now your use bit is 0. So if you are not accessed in near future, next time you will be swapped out. It's like giving a warning to someone before taking a serious action. You can understand like this. That is why this algorithm in literature also it is called a second chance algorithm. It's also called second chance algorithm. So in that process, whichever frame is encountered with use bit set to 0, whichever frame is encountered with the use bit already set to 0 is selected for the replacement. It is selected for the replacement, like whichever whichever frame is having use bit 0, this first it is encountered, it will be replaced. Okay. So let's look at the example of clock policy. So again, I'll try to trace the example here. So before that, just keep in mind this notation. So here this asterisk sign is use bit. So when I have an asterisk bit, when I have asterisk setup, when I have asterisk setup between some frames, it basically means that you have a use bit set. So let's start with 2. So when 2 is brought in, its use bit is set. Then 3 is brought in, its use bit is set. And again 2 is brought in. So already its use bit is set. So you don't need to do anything at this point of time. Then 1 is brought. So its use bit is set and pointer is here. So you see, this is also, there is a concept of pointer because we have to traverse one by one each frame. So whichever frame you are setting, the pointer moves to the next frame. Whichever frame you are setting, the pointer will move to the next frame. So now till here, everything seems okay. Now here we have to insert 5. So definitely 5 is not there. So it will be page fault. But how the algorithm will proceed? See, so it is here at 2. So let me take a separate way like this, right? 2, 3, and 1. Okay. So what it will do, as per the algorithm, it will see that can I replace 2? The answer is no because use bit is set. So what it will do? It will cancel the use bit and move to the next location, right? It will move to the next location. Then here also it will check, can I replace this? The answer is no because the use bit is already set. So again, what it will do, it will just discard the use bit basically and move ahead, right? So I have to just move ahead, come here. Again, it will see, can I replace this? Answer is no because use bit is set. So again, make this use bit 0 and move ahead. So now ahead means I will just come back here. Now this is the first frame it has encountered with use bit 0. Can I swap this? Yes, because its use bit is set to 0. There is no asterisk sign. Use bit is 0. So what it will do? Instead of 2, it will insert 5. Instead of 2, it will insert 5 and the pointer moves on to the next frame, right? And 5's use bit is set because it is just brought into the memory. So if you see, this is the state, right? That's how we encountered this particular state. Okay. So you can see that the process is little lengthy, but it makes sure that all the frames gets all the pages gets a second chance, and no pages are no pages are you know kind of getting replaced without one chance, without warning. Let's trace one more. So now the pointer is here. Next reference is 2. So 2 is not present here and the pointer is here. Now can I swap 3? Answer is yes, because 3's use bit is 0. So instead of 3, I will put 2, make it asterisk sign, and then my pointer moves here. The next reference is 4. The 4 is present here. Answer is no, 4 is not present. Can I swap 1? Answer is yes, because its use bit is set to 0. So I'll swap 1 and insert 4, and pointer moves here. Okay. And whenever some pages are not found, I will just kind of count it as a page fault. Then next is 5. 5 is already there, so no need to do anything. Then 3. 3 is not here again. So 5, 2, and 4. What you will do? You will make a full circle. Set use bit of 5 to 0. Set use bit of 2 to 0. Set use bit of 4 to 0, and then come back to 5 and swap it. So 5 is swapped out and 3 is inserted, and pointer is moved here, right? Next is 2. So this is interesting. See, this is interesting. 2 is already here, but 2's use bit was 0. 2 is already here, but 2's use bit is 0. So I will set it to 1 now. I will set it to 1 now. So make it star, and pointer will remain as it is because it is just making a asterisk sign. Next is 5. So again 5 is not here. So I will again make one circle. 5's use bit will be 0. 3 is oh sorry 5. Okay. So I have to insert 5. So I will come to 4. Can I replace 4? Yes, because 4's use bit is 0. So I will set 5 here. And next is 2. So again 2's use bit is set to 1. So you can see the number of page faults here is 5, and page fault rate is 5 out of 12, right? Yeah. So what is the page fault rate here? If we take 5 by 12, it is 0.41. So it is 41%. 41% of page fault. So if we go back to our comparison, we can write one more column here. Clock policy 41. So you can see that clock policy is kind of somewhere between LRU and FIFO, right? Means that it's not as bad as, not as good as LRU, but also not as bad as FIFO. Something between them. So definitely no one can match the optimal policy, but if you want to kind of go nearer to it, you can use these policies before LRU and clock policies. So again, this is just a what do you say, circular illustration of clock policy. So it uses the circular pointer, concept of circular pointer, that we are not discussing. So this is a complete example of FIFO LRU optimal and clock policy, and how they are kind of impacting the performance in terms of page fault. So we are not discussing all these things. Now we'll directly discuss the page buffering. So see that in our scope, we have to only discuss the basic working of clock policy. We are not going to include the detailed analysis. So what is page buffering? So as you know, LRU and clock policies both have complexity and overhead. So on paper itself, we find it difficult to trace. So if we implement it as a system, definitely it's going to take a lot of overhead. Also, replacing a modified page is more costly than unmodified because it needs to be returned to the secondary memory, right? So always when some page is already accessed and when some page is already uh, modified by the user, it is difficult to replace that page because before it is replaced, you have to make sure that you perform the disk write operation. So to solve all these issues, we have a concept called page buffering. Now, what is page buffering? So in case of page buffering, we don't go into more complex replacement algorithm. We only use the simple FIFO algorithm. But when we replace a page, when a particular page is replaced, it's maintained in one of the two type of lists. Is maintained in one of the two type of lists, and those lists are called free page list and modified page list. The type of these lists are free page list and modified page list. So what is the meaning of free page list? So when a page is replaced and is not modified, when a page is replaced but it is not modified, it is appended to this list. It means that this page was replaced, but it was not modified by the user. So you can easily discard it. However, the second type of list is more crucial. That is modified page list. So when a page that was replaced is modified by the user, its content, its data is modified by the user, then it's called modified page list. And that kind of page, when it is replaced, it is added at the tail of the list. It is added at the tail of this list. The replaced pages are not just removed from the memory. Only their entries are removed from the page table. So it's like fooling a memory, right? You are not actually what should happen when you replace a page, that particular page should be removed from the memory, right? That particular page should be removed from the memory. But here what is happening, you are not removing it directly. Instead, you are only removing its entry from the page table. Otherwise, physically, this page is as it is in the memory. So it is called page buffering. So definitely page buffering has advantages. So if the process refers to a page that was just replaced, can be fetched quickly, right? Because the page was never actually removed, right? Because the page was never removed actually. That is why you can easily bring it back. So that is the advantage of page buffering. Also, modified pages can be written out in batches, right? Modified pages can be written out in batches. So instead of writing one page to the disk, you can do the disk write operation in bulk. That is the second advantage. So basically, free and modified page lists are acting as a cache memories. So in case of page buffering, you should notice that we need more memory. because we said that we don't actually replace a page, we have to just remove its entry, but the original page, actual page is there in the memory itself. So you require some more memory to store such cached pages. So note that buffering requires more memory. That is the advantage, that is the disadvantage. So more memory is required in case of page buffering. Its advantage is that your overall execution may be faster, because whichever page you assume that it is replaced, but it's already there in the cache, you directly get it. Right? Same meaning of buffering is same, right? When you look at when you watch a YouTube video, what is the meaning of buffering? Already some portion of the video is pre-downloaded. So when you require it later on, you can directly get it. Otherwise, what will happen? You have to keep waiting till the video is loaded. So the same concept comes in the page buffering. Okay, so I think that is enough for today. We stop here, and in the next lecture, we'll take the remaining topic with few examples of page replacement as well as the overall virtual memory. So from this today's session, most important topic you should consider is page replacement policies, FIFO LRU, and clock policy. You can look at the example again in detail and try to solve it yourself. Apart from that, if you have any other doubts, we can interact in next few minutes. Okay, I guess we stop here.